And then this hour, going to be speaking to the head of physics at one of the grammar schools here in Essex. Keith Dalby is going to be here. He's going to be talking about physics. What is physics? Does anyone know? Hopefully you know more than me. Well, let's find out more about physics. Also, about his YouTube channel. So, Keith is the Joe Wicks of the physics world, because during lockdown, he went on the internet and set up a free YouTube channel to help people, free of charge, to help them with physics. And it grew in popularity, and I think he's still doing it. So we'll find out more this hour as well. And before that, we've got something a little bit different. We've got the Joe Wicks of physics here in the studio right now. He's going to be on after the next song. He's Keith Dalby. He's the head of physics at one of the best schools in Essex. He's going to be talking about his YouTube channel, Physics with Keith, which is free, some free classes to help you learn about physics as well. And we're finding out what is physics. Physics wasn't my favourite subject at school, but maybe it will be after tonight's show. Who knows?
Nita Jhummu's City Talk.
The time now, it is 20 minutes past 8. My name's Nita Jhummu. This is City Talk on CCR on 104.4 FM right here in Chelmsford until 10 p.m. this evening. Talking about love after 9 o'clock if I don't chicken out. Yes, we're going to get some people in to help me talk about that. But right now, talking about something completely different for Valentine's Day. Here with me is the head of physics of Westfield High School for Boys.
Close. Sorry, it's Westcliff.
Westfield. I said, why not? I've got shopping on my brain, haven't I? So, should I start that again? Right. Pretend I didn't say that. Right. Joining me right now is the head of physics at Westcliff High School for Boys, Keith Dalby. Good evening.
Good evening.
Hello, how are you?
I'm very well, thank you, yeah.
Thank you for coming into the studio on Valentine's evening.
Yeah, I didn't have any other plans.
But your wife is out there. She's outside.
Right.
So that's so nice of you to come in, and your wife as well, to be here with us at Chelmsford Community Radio this evening.
Well, she couldn't resist coming to see me make a fool of myself, which is always good fun.
Well, I got the name of your school wrong already. I never really get things wrong. I don't know what's happening tonight. But you are the head of physics at Westcliff, and also during lockdown you set up your YouTube channel, which is Physics with Keith.
That's right, yeah.
During lockdown, which has gone really well, and people following, people joining in, and it's free as well, so you're giving free advice as well, and you've got lots of experiments and tools and things here with you tonight, which is really, really cool, and I can't wait to see what this concoction is going to do a little bit later on. But
try and blow your mind a little bit, I hope.
Yeah, I hope so. So physics, I think I mentioned before, wasn't my favourite subject at school. I've got a maths degree, so it's not totally unrelated. I liked history as well, but I'm wondering if it was because of the teaching maybe at the time, or I don't know really, because I'm old enough that when I was at school we couldn't have had like your YouTube channel, because like the internet was on dial-up and it was like really slow, and it used to be really expensive, really slow, and it used to make those like winding like telephone noises.
Yeah. Of course, YouTube didn't exist, and Google didn't exist, and Wikipedia didn't exist.
Sound really old now, don't I? And mobile phones, even like then, they were bricks. They had like aerials on them, and you could only text. You couldn't do pictures and videos and all sorts of things then. So, do you think that's helped?
I think it really has. I think back to when I did my degree. Mine's physics, obviously, but how much easier would it have been if I had all those tools while we were studying? It would have changed everything, having those tools at our disposal. I don't even remember teachers giving out past papers or anything like that. It just wasn't done, was it?
Really? I think we had some few past papers, I think.
Might be the school you went to.
I think we had some past papers, but yeah, computers, we didn't use it to the extent people do now, really. Lots of things was written, so yeah, I wonder what happens these days, and if people are used to handwriting as well. But let's go back to basics. So physics, when you think of the three science subjects, so at school, I don't know if it's still the same, you do chemistry, you do biology, you do physics. So chemistry is like lotions and potions, concocting things. It's really simplistic, as you probably could imagine. Biology is the body. Physics, what is it? What is physics?
Yeah, so I've got a bit of a joke within my school. I've got a club for year 12s and 13s, and we've got a special club that we run on Wednesday afternoons, and we call it the Studies of the One True Science, because that's what physics is to me. It's the science that underpins all of the other sciences. So you can understand the mechanisms of biology if you understand chemistry. Biochemistry is what drives how the cell works. It's all about what the chemicals are doing.
Right.
And you can understand chemistry if you have a firm grasp of physics, which is all about forces and energy and the interactions between particles and that sort of thing. So having a really firm grasp of energy and forces means you can make accurate predictions about what's going to happen in that test tube when you do chemistry. And in the same way, if you have a really firm grasp of what happens in that test tube when you do chemistry, then you have a better grasp of what happens in biology. And I could go a step further and say, if you understand biology enough and understand how the brain works, then you can understand psychology, and then if you understand that, you can go on to sociology, and if you understand that, then it's philosophy. And so it really is, from my perspective, it's the science that underpins everything else.
So that's why it's the one true science.
The one true science. It's deliberately provocative, but I don't know. Most of the physicists that I've met enjoy being provocative, so that's that's not surprising to me.
So one of our listeners has messaged in and saying that physics is the natural science, I don't know if this person's looked it up right, of the study of space, time and entities of energy. Is that kind of right?
Sure, that's fine. Yes, space and time and energy and forces and the interaction between matter. And what makes science as special is that it's all about predicting, making models that make predictions. That's what it's all about. There's a sort of a common misconception that science is trying to find the answers to questions like, why does this happen? And we don't ask that question. That's not part of science. What we ask as a question is, how do these things happen? And what will happen next if this is the thing that has happened? So we make models, mathematical machines, where we put in a map of a picture of what currently the situation is into this machine, turn a big handle, and out pops a prediction. And then we do an experiment where we put the same input parameters in, watch what happens, and see if our predictions are correct. And if they are, then we all celebrate and get Nobel Prizes. And if they're not, then we all celebrate and we get Nobel Prizes, because the whole point of it is to improve our understanding. And that only happens when things don't work out the way we expect them to.
So what's the difference between that and what some of the stuff I've done in maths, modelling and things?
No, there is no difference. Absolutely no difference. And this is the fun thing. With A levels, we really focus on the difference between these subjects, and we jest and we rib each other about the differences between the subjects. But then when you get on to doing a degree, and you might remember this from when you did your degree in mathematics, there is a tremendous amount of overlap. So in physics, we will use mathematics as a tool. And chemists will use physics as a tool, and so on, as tools to make those predictions. The difference between mathematics and physics, the big difference, is that physics is concerned with what is measurable. So we don't end up with beautiful whole numbers and surds and irrational numbers that just seem to work perfectly. We don't end up with that. We end up with dirty numbers because the universe doesn't play along with us the way we expect it to. Every measurement you make has some degree of uncertainty to it, and so our machine has to handle that uncertainty. And mathematics as a tool is very pure, and whatever numbers you put in, you will always get the same outcome if you've done the maths right. But that's not the way it works in physics, because the universe doesn't work that way.
That's really interesting. I hadn't thought of it that way as well. That's something to ponder.
There's a lovely quote from Richard Feynman where he said, Richard Feynman's a physicist. He's dead now, I'm afraid. He died quite a few years ago. But he was responsible for changing our understanding of antimatter. He had a wonderful way of viewing antimatter as matter with a backwards arrow of time. It's fascinating. But anyway, Richard Feynman's got a lovely quote where he says, if you don't like the way the physics works in our universe, then leave. Go to a different universe where the physics is more pleasing to you. And I think there's something really lovely about that. We find students that really don't enjoy it and they don't get on with it, and you say, okay, no, I understand that, but it's the way it is. And if you can make a model that predicts better and is more pleasing to you, great, go for it. Otherwise, the best models we've got at the moment are the ones that we work with.
I see. And what are the branches of physics?
Okay, so we could start with a sort of pure and applied physics that links quite nicely to engineering. So that's quite mathematical based. It's very much about models. Some of my favourite branches are particle physics and quantum physics. Big fan of that. We can start looking at things like thermodynamics, which again links quite nicely with engineering, looking at how energy is transferred around as a sort of an abstract concept rather than something tangible. We've got electromagnetism, and you can see some of the toys I've brought here are magnets and things like that, because magnets are fun. Physics is fun. It is fun. We've also got things like space. We've got relativity, we've got and then we've got some more mundane things like the gas laws, but then if it wasn't for the gas laws, we wouldn't have things like rockets. We wouldn't understand how rockets work and why you have to have heat shields when you re-enter. So none of the branches of physics really stands independently of any other one. The thread that runs through them all is this idea of forces and energy and making sure we can, as I say, create models to make predictions.
Some of that sounds really fun. Space, relativity. So if time travel was to be invented or happen, maybe somebody is time travelling right now, we wouldn't know. Would that be a physicist that cracks that?
Well, I don't think a physicist would want to time travel when they've figured it out. I don't know. I won't speak for all physicists. Now, the fun thing about time travel is that you're doing it, and you know you're doing it. Everyone knows they're time travelling because they look at their watch hand and they're moving. They understand they're time travelling. And within special relativity that you'll learn in high school, there's mechanisms to travel forward in time. That's all quite straightforward physics now for high school students. The tricky thing is the idea of going backwards in time. And there's no model, no machine that we can put our current understanding into, turn a handle and out pops backwards going backwards in time. Now we have got the idea of going backwards in time as an explanation for some of the things we've seen. For example, antimatter, trying to understand antimatter. Actually, if we consider it to be particles, but they just happen to be going backwards in time, it does actually help with the maths. But there's nothing we can do with it. We can't make a time machine out of it yet. And so going backwards in time, that's the challenge. And from the latest that we know is that is just not possible because of the absence of some exotic matter that has negative mass, which has never been observed. And if it did exist, it would break a lot of other parts of physics, which is exciting. We like the idea of breaking physics. It means we can make more physics. Keeps us in the business. So
does that mean, like in the films, that you go back in time and then you change the course of history and then come back to present and it's all gone wrong? So because it's not been done, or at least we don't think it's been done, we haven't got any empirical evidence of it, we can't know. So there are some lovely philosophies about if we could go backwards in time, then what would happen? And it rather depends on things like your interpretation of quantum physics. So there are two main... I'm going to waffle now. There are two main branches, two main interpretations of quantum physics. One is the Copenhagen Interpretation. And in that interpretation, there are possibilities of things happening. And when you observe something happening, you collapse those possibilities into a single thing that happens. And you can't go backwards. That's it. That's happened. The alternative is the many worlds interpretation. Well, there's a few alternatives, but another alternative, a very popular one, is the many worlds interpretation. Now, in that one, there's lots of different realities, and every possibility exists in some reality. And the reason why you observe certain realities is because you end up becoming entangled with those probabilities, with those realities. Right.
Now, in that philosophy, then it should be possible to, I'm talking absolute nonsense now, untangle yourself when you're going back in time. I don't know. None of this is being done, of course, and there's no way that we can do it with our current understanding of physics. But what's interesting is that both those interpretations of quantum physics, the many worlds interpretation and the Copenhagen interpretation, both of them make the same predictions of what we should see for the input parameters. And so there's no way of knowing which one is right or which one is wrong, or even if they're both wrong or both right, or something else altogether. They're interpretations.
Okay, all right. It happened in Back to the Future, didn't it?
Well, yes, but then the time travelling Back to the Future is different to the time travel you'll find in other films. So, for example, I've seen bits of the film Interstellar. I haven't seen the whole thing. The intro was far too long for me. No, I haven't seen the whole thing. But I understand the time travel in that is much more deterministic, where you can't actually affect the future by something you do, because that future lies along a deterministic path. Whereas in the Back to the Future films, Marty McFly's parents are very different when they return, having changed the past. So that's a completely different style of time travel.
And it's the Doc a physicist.
Is the Doc a physicist, or is he a lunatic? I don't know. I mean, if you throw some fancy sci-fi words together, then it could sound like physics, can't it? Flux capacitor and things like that. But
88 miles an hour.
But no, he's a plot device, isn't he? That's what it is. I know, I'm sorry.
No.
Time travel. The thing is, we don't need it. Sci-fi is lovely and exciting, but it is there for entertainment, and the physics is exciting enough as it is. The fact that we can go forward in time is exciting as it is. The fact that things like the twin paradox, I don't know if you've heard of the twin paradox. This is one of my favourite bits. So according to relativity, if you are moving relative to something else, then you will observe their clock running, let's try that again. If something is moving relative to you, then you will observe their clock running slow. So an event in a moving, what we call a reference frame, let's imagine a rocket ship moving past us, an event in that rocket ship will be running slower. Okay. So if they say hello to you, you'll hear it in slow motion. Okay. But in their reference frame, they're not moving, and you're moving backwards. So in their reference frame, when you reply hello, they think you're talking more slowly. So each person sees the other person's clock running more slowly. So what the twin paradox says is, imagine we've got two people exactly the same age. Yes. One of them gets in a rocket ship, flies to a distant planet, turns around and comes back. Now, from the person who stayed on Earth's point of view, they've not moved. The other person's been moving, so their clock is running slower. So when they arrive, they shouldn't have aged as much. So they should be younger. But from the point of view of the person on the rocket ship, it's the person on the Earth that's moved backwards, turned around and come back. So their clock should have been running slower, so they shouldn't have aged as much. So when they meet again, which one's younger?
Ooh,
now, there is a lovely solution. It's to do with looking at different reference frames and how...
Is it a trick question?
When you... Well, sort of. When it's not really a paradox. If you're the outgoing person on a rocket ship, then in order to turn around and come back, you've got to switch onto a separate reference frame. And it's true that in each reference frame, the clock appears to run slower. But when you switch across from an outgoing to an incoming reference frame, you skip over a part of the time. From the point of view of the person on Earth, you would see the person on Earth suddenly leap forward in age. So the person on the rocket ship would end up being younger when they arrive.
Really?
Yeah.
How did someone come up with this?
Well, you can thank Einstein for that. And I can draw a Minkowski diagram for you if you like, but it's not going to help the people listening at home. But no, this is the sort of thing. So physicists have worked out loads of fun stuff that you can do without having to have the sci-fi part. This is all real. This is the thing that really gets you with the special relativity. We know it's real because it's our explanation of how magnets work. Something as fundamental as a magnet needs relativity to work. But not even that. We've got things like GPS orbiting the Earth. Satellites orbiting the Earth. And those satellites orbiting the Earth, if we did not take into account the principles found in relativity, then we could not use them to triangulate our position, because they're all moving relative to the Earth. There's some general relativity here as well. They're further away from the Earth, so there's another effect to do with time there. But when you put all of the physics we've got from relativity together, we can use those satellites to predict where we are on the surface to within a metre or two. Whereas if we didn't take into account relativity, that wouldn't work. So we know relativity works, and it has all these really exciting consequences, like magnets, like time travel, like cosmic microwave background radiation, which is showing us the very earliest parts of the universe that it's possible to see. The moment the universe became transparent, we can see that, and we understand that because of redshift. But cosmological redshift isn't caused by what you might have been taught in school about light stretching out as it moves away. It's nothing to do with this. But we have this cosmological redshift, which we can explain using relativity, and using that we can figure out things like the age of the universe,
right?
Why galaxies are clustered the way they are.
So people should be making films about the real life things that we know.
Oh, they do. They do. They just don't sell as much as people getting in a DeLorean and going back and falling in love with their mother or whatever the film was about. I didn't pay much attention. It's Valentine's Day. Maybe that's the appropriate thing to talk about.
Right, let's take a break now. Let's play a song. A choice of yours, actually. You wanted Gary Newman and Our Friends Electric quite appropriately. After which, let's talk more about your Joe Wick style podcast that you've done, YouTube channel with physics, Keith with physics, and also let's crack on with a few experiments as well.
Yes, let's do that.
Yes, experiments on the radio. Such fun tonight.
Broadcasting from the home of radio. This is CCR. This is CCR.
It is 8:45. It is Monday, the 14th of February 2022, Valentine's Day, and Keith Dalby, the head of physics at Westcliff High School for Boys, is here in the studio with us. Thank you for being on the show on Valentine's Day.
Much. This is great.
So, Keith, you have, in lockdown, actually, you come up with a YouTube channel, Physics with Keith, to share your knowledge about physics and to give free lessons, basically. So how did you come up with that?
Well, I saw on Facebook there were my fellow teachers posting messages saying, if there are parents, you might have seen the messages from other teachers, if there are parents who are finding it difficult during homeschooling and they need any support, drop them a message, they'll help explain anything. And I saw that and I thought, I can do better than that. I could actually do this. I could run some lessons. So I started it up really for that reason, so that there was a sort of an online series of lessons. I didn't want to just do videos because there's a lot of that on YouTube already, so I decided to do it as live tutorials where students could ask questions and then they could give answers, and it would be like a virtual lesson, the sort of thing that we were getting as teachers very well trained doing during the various lockdowns, doing the online learning, but just extending that out so that anyone who is in the same sort of situation would be able to benefit from it. And then after the lockdown started winding up, I got quite nervous and thought, there's all this lovely skill I've learned how to use, this online learning, and I don't want to lose it because I quite enjoyed it. So I thought I'll carry on offering it. And that's where I'm at the moment. I want to carry on offering it. When
are your classes?
My classes are on Thursdays at the moment. They're always flexible, but they're on Thursdays at 5:30, and they're an hour long. And you can interact via YouTube. You can watch via YouTube. If you want to ask questions, you can go on to, there's a Discord server, and the links are all on the website as well. But the thing is, I saw a lot of people getting tutors. I've been teaching for a long time now, and people pay a lot of money for tutors. And I decided I wanted to do this for free because I'm not a big fan of the idea that someone who can afford to pay more money should somehow get better chances or something like that. It made me feel uncomfortable. So I thought, I'm going to offer this for free so that everyone can benefit from what they're seeing.
Especially in lockdown when we saw the inequalities and people's home situation, some people not having tables and chairs facilities not right,
or you've got 4 children at home and 1 computer between them, and yet they're all supposed to be there for online lessons. Well, how does that work? So I was just trying to do something to make it so that physics can keep up, so that people don't lose any learning or fall behind in their physics.
So if anyone listening right now wants to join in with your lessons, they can.
So I've got students as young as year 7 who tune in regularly, and they do very well. I've got a 12-year-old who really keeps up with all the work, all the way up to 18 years old.
So there's no age limit?
There's no age limit, no. What I tend to do is try to have the first part of the meetings sort of generally GCSE friendly, and then towards the end we bring in some more A-level stuff, and there's lots of questions there, and I try to make sure there's plenty of interactivity, not just watching me lecture.
All right. And how many people join in with your classes?
Yeah, so we get a few coming in quite regularly. Every now and then someone new turns up. So I've got something along the lines of 880 subscribers nearly, something close to that on YouTube. And I get maybe 10 people watching live. Now, I do understand a lot of people do watch afterwards, but about 10 people watch live and join in regularly. Which, okay, I mean, even if it was one person, I would still do it because I enjoy doing it and because it's the right thing to do.
Yeah, and it's all about building up as well.
There's that as well, yeah.
Yeah. And are your students listening tonight?
I would hope so, yeah. Yay. I know a lot of my students do live around this area. Hello, everyone. I know a lot of my students do live around this area. And I have told them all about it, so I hope they're tuning in and they will embarrass me and make fun of me. And it's all good fun. That's what teaching's all about.
Yeah, I've seen pictures of you on your YouTube channel and with information about you, about dressing up with, as a robot in school and as a genie or something. And do you do that often?
As often as I can, yeah. So that's the charity pantomime that our school puts on every year, although for the last 2 years they've not been able to because of not being able to have as many people in the hall at once. But we're getting back to something that looks a bit more like normality now, so I'm looking forward to getting dressed up or painting my face blue again or something else.
Cool. I think we should do some physics experiments live on the radio.
Yes, this is definitely going to work.
This is so much better than when I was at school. I don't remember doing many physics experiments, to be honest. There was a few chemistry, mixing of tubes and things like in a test tube, but I don't remember physics, like doing much of physics. So this is really cool.
Now, chemistry tried to steal the limelight because they can make things go bang, but we make things go bang in physics as well, don't we? Yeah. So I've got here a copper tube in my hand. Ooh, and I showed you this just while Gary Newman was playing. Yes. Copper's not a magnetic metal, and I can prove that to you by the sound you can hear is a magnet banging against a copper tube, and nothing is being attracted, happening. But it's definitely a magnet. Yes, can you confirm?
I can confirm it's picking up.
Big iron bar. So the copper tube is not magnetic.
No, it isn't.
And if I were to drop this pellet of steel through it, and it's got a slice down the side of the copper tube, you can see how fast the pellet falls. Oop, I nearly dropped it. Can you confirm it falls very quickly?
Yeah, it's so quick that you're having to.
I'm really rushing to try to catch it. I've got another pellet that looks identical. It's the same size.
Same size.
The only difference is this one is magnetic, and if you can see, it is not attracted to the copper.
No.
But when I drop it down the middle of the tube,
it goes really slowly.
Really slowly, but it falls much more. It takes many seconds to fall through a tube, which is about 30 centimetres long. And the reason for that is because although copper is not magnetic, when there's a changing magnetic field nearby, it does become a magnet. Just for a moment, it becomes a magnet itself. And actually all materials do this. There was a rather unkind experiment done, and I'm not going to promote it because it was rather unkind, on a living frog, where they made the frog levitate in a very strong magnetic field.
Right.
And I'm going to show you why I'm not so keen on that experiment now. So could you just take hold of this copper ring and just confirm it is not that hot?
No, it's a
sort of normal room temperature.
Normal room temperature, neither hot or cold, really.
Okay, so that's a complete copper ring, and I've got here an iron bar, and in front of me, connected to a 24-volt AC power supply, is a 300-turn coil. And if I just drop the copper ring on that, it falls straight through. There's no magnetic force.
No.
But when I put... Where's my copper ring gone? There it is. But when I put put a current, an alternating current through the coil, you can probably hear that buzz. I don't know if you can hear it at home. There's a buzzing at about 50 hertz where the iron is now being turned into a magnet, on and off and on and off and on and off in alternate directions. If I drop the coil on there, the ring...
Oh... It doesn't want to go down.
It doesn't want to go down. It levitates.
Yeah.
But there's other exciting things we can do. So we can take a second ring, and if I drop that slowly on top of it...
Oh, it's like...
So you can see the bottom ring is attracted up towards the top ring. Even though copper is... Not magnetic.
No.
But it's behaving like a magnet. It's becoming temporarily magnetic. Now I'm going to leave that there just for a little while. In fact, I don't have to leave it there very long, and you'll feel the difference. That copper ring is starting to warm up. In fact, I'll lift it off now because I don't want you to burn your hands. We just have a little feel.
Oh yes, it's warm now.
Yeah. So the reason
actually
it's quite hot, isn't it? And that was only for a small period of time, and that's why I think the experiment on the frog was particularly unkind.
Oh, what happened to the frog? Did it get...
Well, from what I've read, the frog was unharmed and hopped away. And
That's
I'm
good.
happy to say that I have not seen any further of these experiments, only that one. So
Poor frog, it could
pretty-
get blown up, couldn't
well,
it?
I'm pretty opposed to animal testing. It's not something I'm a fan of at all.
Oh.
Do you want to see something a bit more visual?
Yeah.
Everyone at
Yeah.
home on the radio.
Okay. On the radio, visuals on
What
the
I've
radio.
got here, this is a spectrometer, a little
Right.
handheld spectrometer. And you look through this end here, directly at any lights you can see. So if you look through it,
Oh yeah, you can see a rainbow.
you can see a rainbow.
colours
Now,
when you look at lights.
Absolutely. So you can see the full spectrum of colours. And
Yeah.
a device very similar to this you can use to determine the atmospheric composition of exoplanets. They're planets that are orbiting stars other than our sun.
Right.
If you get the light from a distant star just skimming through the atmosphere of an exoplanet, and that light you pass into an instrument a bit bigger and a bit more sophisticated, but with the same physics principles as the spectrometer you've just held in your hand, you can see that there are certain colours missing. And you won't be able to see it with this, and these lights are producing a pretty good white light. But if you try and focus it on the red of that clock, so I'm just pointing at a clock in the
There's a
corner
clock.
of
We
the
have
studio.
a clock in the corner of the studio.
If you point it directly at it, you really do have to get it directly lined up, and you'll only see the red line.
Oh, this is. I can't
It might be
quite
difficult to get it perfectly
Yeah.
lined up. You might have to move a bit closer. But when you get it perfectly lined up, you can only see that one
yeah.
colour. So if you look with a very, very sophisticated instrument like this at the Earth's atmosphere, there are certain colours that are missing. If you look towards the sun, for example, there'll be less blue
Right.
than there would usually be. And that's because the blue light is being scattered in all directions. That's why the sky looks blue. So if you look at the atmosphere of an exoplanet, and if you can imagine how far away these things are and how precisely you have to aim these instruments, we have to put them in space to make sure there isn't atmospheric disturbance messing up what we're looking at. But you can work out the composition of these planets, and it's using that sort of technology that we've found planets that have an atmosphere that could support life.
Brilliant.
Now, they're quite a long way away. They're about 1,120 light years away, which means it would take about 1,120 years for a radio signal from us to reach them there. So this fantastic broadcast won't reach there for another 1,120 years. But if you think, we were sending our radio signals into space for the last 120 years, roughly. So in about 1,000 years' time, our first radio signals will be arriving at this planet. Now, we don't think there's intelligent life on this planet. There's no reason to think there is. But if there was, and they had the technology to detect our radio signals, as weak as they would be when they arrive, then they would know that there's intelligent life here. And then maybe they could direct a radio signal back in our general direction. And so in another 1,120 years, we might actually know that they're there.
Excellent. And it's the power of radio. Yay.
The power of radio.
Yay.
There it is. Yeah.
Yes. We are
so-
the birthplace of radio.
The birthplace of
course.
radio,
We're in Chelmsford.
absolutely. But so you can actually make a device like this yourself at home. So I've just got a pile of wire here that I've, because I knew I wouldn't have time while I was on the air, I did this in advance. I've got a lovely coil of wire here. It's just any old wire like you can get
Very
from
Blue Peter.
yeah, anywhere you want. It is very Blue Peter. And I've got here a battery. I'm just holding up a battery. It's 4D cells, so 1.5 volt batteries in a little caddy. And if I connect these like this, so I'm just connecting with some basic crocodile clips. All of this stuff you can buy from, I'm not going to say any retailers in case I'm not allowed to advertise them, from common hardware shops, and get a piece of iron in the middle of that. Now, that is actually an electromagnet.
Right.
It's just a coil of wire, but it is able to pick up things, and if I disconnect the magnet, it drops down. So it's possible to make yourself electromagnets. And the bit that this is what absolutely blows my mind is the physics here in this electromagnet relies on special relativity that we talked about earlier. It relies on the idea that because charge is moving, the distance between the charges becomes contracted, so that the charge appears to be, well, so it's not a neutral wire anymore from the perspective of a moving charge.
Right.
So that means that the environment inside my hands here, it appears differently depending on whether you are moving relative to it or if you're not moving. If you're a charge that is moving, then you see something that is charged. And if you're a charge that's not moving, it looks like it's not charged. And both realities are true. This is both charged and not charged, depending on whether or not you're moving relative to it.
Wow. Okay. Cool. And it's really...
It is exciting.
It's exciting, and it's just... like you said, you can do that yourself.
I can do that with myself with just some batteries.
I was a bit scared when you were like putting those crocodile clips on, but it was like quite cool.
You don't need crocodile, just wind a wire around them. And of course, if you want to do something, I mean, that's now getting too hot to touch. Turn that thing off. I can't actually hold it.
Be careful.
Hopefully it's not left a burn mark in it. No, it's okay.
Burning the studio, everyone.
Burning your studio. But what you can't tell, I've just left the electromagnet on with the 24 volts AC, and the iron bar has become so hot now that I can't pick it up. That's the power of physics.
Oh, but on that note, thank you so much for coming on City Talk tonight. It's been a pleasure.
More toys. Okay.
Oh. You'll have to come back and do some more.
I'll definitely come back if you invite me.
Thank you so much. Thank you so much. So, for anyone listening who wants help with physics and to join in your classes, or maybe they know someone that they're thinking, hang on, I know such and such person might benefit from this. What are the details? Where do they need to look?
Yes, so if you go to physicswithkeith.com, all the details are on there. You can all search for Physics with Keith on Facebook or Twitter or Instagram. I'm on all the social media channels. And there's links there to the YouTube channel and also to the Discord server so that you can get registered. And I do need to point out as well that I do go slower in those sessions. I'm trying to cram quite a lot in here, so I don't usually go quite as fast as I have today.
Yes, you can ask lots of questions and clarify things. Thank you so much, and I hope you enjoyed your experience on Chelmsford Community Radio tonight.
I had a great time. Yay. I really did. It's over too fast.
Yes, thank you so much for bringing in all those experiments and letting me see them as well. I wish I had you as my teacher when I was back at school. I think I would have loved physics. I don't remember doing any of these things.
You're flattering. Very, 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 very kind of you to say so. Thank you.
Yes, and thank you to your school, Westcliff High School for Boys, for letting you on tonight as well.
I'll ask the headmaster for a pay rise.
Yes, and the recording will be available as well, so you can share it out as well. Right, thank you so much for being on tonight's show.
Thank you very much.
Let's get our first request on for the night.